Welcome. My name is Anke Hagen. I'm a professor at the Technical University of Denmark, and today I have the pleasure to give you a very short introduction to catalysis. In this presentation, I will start with a short explanation what is catalysis actually. I will talk about interaction, activation energies, and I will talk about reaction kinetics. Let's start with what is catalysis. So I like to illustrate this with this picture. You are a hiker, and here you have the restaurant that you would like to reach. And you have the option to go all over the top of the mountain. This requires quite a lot of energy and strength. It might take a lot of time. Maybe the restaurant will be closed at that time. But luckily, you also have another option. And that shows you the easy path is the red one that also arrives at the restaurant. However, you don't have to overcome such high mountains, so you could actually reach faster to the restaurant. And that we actually can translate to catalysis. The hiker is the reactant, and the restaurant is the product you would like to obtain. And then you can draw an energy diagram. So here you have the reaction path and the energy in the vertical axis. You are starting from your initial energy, and you would arrive at the final energy. And if you only have the one option over the top, then this is the activation energy without a catalyst, which might be very high and you might not be able to overcome. However, when you introduce a catalyst, this actually provides you this red path where you lower the activation energy, and in that way you might be able to reach your goal to obtain the desired product. So this is the essence of catalysis. So what is a catalyst? We can say a catalyst does the following things. It affects the activation energy of one or more steps in the chemical reaction process. A catalyst changes the rate of the chemical reaction, means you can be faster in the restaurant. The catalyst is not consumed by the reaction, so you have it at the end as well. On the other hand, you have to note that a catalyst does not change the thermodynamics of your reaction, and it can also not induce or create a reaction that is not possible by thermodynamics or by nature. So in other words, if there is no restaurant, your catalyst cannot conjure a restaurant. This is catalysis. It is a lot about energies, activation energies, and I now draw that in a different way. Here now we have only energies and chemical compounds. A very easy case, we are reacting compound 1 with B, A and B, react to the final product AB, and you have to overcome an activation energy. The reaction is very easily written like that, and the reaction rate, so how fast the reaction is proceeding, is expressed or correlated to a reaction rate constant K. And of course, you want to know how are these things intercorrelated and on what parameters do they depend on. And here the famous Swedish chemist Svante Arrhenius found a very useful, very important correlation called after him the Arrhenius equation, which also gave him the Nobel Prize. So you start with expressing the reaction rate. This is a very generic equation. This reaction rate expresses the formation of your product versus the time. And that is correlated with a reaction rate constant and the initial concentrations of your reactants A and B. And how does the activation energy come into play here? The correlation between this reaction rate, fast or slow reaction, and the activation energy is expressed in this Arrhenius equation. Here also the temperature is coming in, the gas constant R, and a pre-exponential factor, a constant factor. So by that equation, you can deduce an activation energy for a specific reaction, and the easiest way is this, what we call the Arrhenius plot, where you plot the logarithm of K versus the reciprocal temperature. You get typically a linear correlation, and from the slope, you can then derive the activation energy. So this is a very important parameter in catalysis. Now, from theory back, why do we at all talk about catalysis? If you look around, catalysis is everywhere. It starts with your body, with nature, with animals. All the productions, your living functions, your muscles involve catalytic reactions in your body. In industry, more or less between 80–90% of all the products we are using in our daily life that are made by industry involve at least one catalytic step. And more important for environmental purposes, we see more and more catalysis appearing, catalysts that help to reduce emissions, catalysts that are removing toxic compounds or breaking them down into less dangerous compounds. So catalysis is everywhere, and it is maybe a bit complex. So how do we get a better overview? We do that by making a few categories, general categories. So we divide catalysis into, here in that case, three different segments. One is homogeneous catalysis. That is the case when you have catalyst and your reactants in the same phase, typically the liquid phase. Characteristics for this reaction or catalysis type is that you are employing rather mild reaction conditions because you have to stay in the liquid phase, so you would be below 100 degrees centigrade. So that is one of the features of homogeneous catalysis. At the end of your process, you have to separate your catalyst from the products and reactants. So that often requires some elaborate extra steps, for example, distillation. A very specific case of this homogeneous catalysis, you can say, is the enzyme catalysis. And that is what is happening in your body often, or in living nature. You have an enzyme that is the catalyst, and that reacts with often very specific compounds. Often only one compound, one reactant is able to assess or access this enzyme to undergo a reaction. Also in this case, we have rather mild conditions in your body. It's more or less room temperature. And this is very special for the living matter, so to speak. And the third category is heterogeneous catalysis. And more than 80% of the industrial catalysis is actually in this category, heterogeneous catalysis. And the main, let's say, feature is that catalyst and reactants are in different phases. What is most often the case is that the catalyst is a solid and your reactants are in the gas phase. That makes it very easy to separate afterwards because the solid stays behind and the gas you can just take out. You can also make continuous processes, just flowing your reactants and products through the catalyst bed. You can also reuse the catalyst. Often this is also connected with more severe or harsh conditions like higher temperatures and pressures. So now you see that we have quite many processes that rely on catalysis, even without knowing it for us or not always being aware of it. Now I would like to draw your attention to a few benefits or interesting features in addition to that reactions are happening, which otherwise would not be possible. There are also economic implications of using catalysis. For example, we would like to have nitrous oxide as an intermediate towards nitric acid, a very important chemical in the industry. You can do this without a catalyst. Then you react nitrogen and oxygen. You have to go to very high temperatures in an electric arc. You use very high amount of energy, and you get only a very small yield, only 2% kind of these gases are converted to NO. When you then use a catalyst, you have to do actually two steps, not just one. You run the first process over iron and then over platinum-based catalysts. However, you can do that at much milder conditions, and you have also a much higher yield of your desired product. So in that way, this the benefit of the catalyst is in particularly here that you need less energy and that you get a higher output of your desired product. That is one feature. Another one is illustrated here. Sometimes you have reactants here as three Lego pieces in red and blue that can be combined in different ways. Like here, I combined them in three different ways. A catalyst can actually help you to arrive at the desired combination. And here for this specific example, I chose the propene oxidation. And depending on which catalyst you are using, you are arriving at different products. I have a bit even more from the same reaction. So propylene, oxygen can react to many products that are interesting final products or intermediates in the chemical industry. And by the help of the catalyst, either of these elements based, you can actually tailor the desired product to be the biggest in the biggest activity or in the highest yield. So you can get the desired product that you want instead of the mixture of everything that is possible. That way, it's also an economic benefit. And economy plays quite a crucial role, and I have just selected one slide here as an example. Here, that is the US catalyst market. You see, alone from the absolute numbers is quite a large number. And here in the prediction towards 2027, there is predicted a continuous increase of the use and production of catalysts. And when you look here in what areas or sectors these catalysts are used, then I have marked the environmental sector, that's the right piece. So that is actually also quite a significant piece, while the others are chemical synthesis, polymers, and petroleum refining. So it is also considering a whole society, the whole economy plays, catalysis plays quite an important role. After this very general warm-up, I would like to go more into detail in regard to activation energy and interactions as kind of the major, let's say, basic concepts or principles that determine catalysis. Let us look at heterogeneous catalysis, as this is the major type of catalysis in industry. So typically you start from a pellet which has centimeters size scale, while a pellet, if you want to use a solid in a gas reaction and you use a fine powder, you would kind of induce a very high pressure drop. So you need a high pressure to get your reactants through this layer. Typically then you make some pellets that could be like in this shape, that the gases are not hindered too much in flowing into and through the catalyst bed. Then when you zoom in, then at the below sub-centimeter scale, you would see there are some channels or pores. And if you enlarge even more, then you see that inside the pores, in this example, it's a noble metal catalyst or particles that are deposited here. And the let's say the trick here is in heterogeneous catalysis, only these parts are active. So all your reactants have to come from here all over down to in contact with the surface and with the active sites. And that the consequence of this is that you have quite many processes going on. Like you have an auto-diffusion, that means the gases that just have to access here. Then you have an inner diffusion, that means within the channels into the pores. Then in the pores, there's an interaction of your reactant with the active sites. Then you undergo the desired reaction. Then you have to go all the way back again, meaning desorption of the product, traveling back through the channels, pores into the gas phase. So this is quite a complex network of elementary steps, and there can be even more details that I have not shown here. Just to show you how it looks in reality, I have kind of photos of the same, let's say, scale. So you have here a catalyst pellet. Then when you zoom with the microscope more and more, you end up at a pore, and here you see some black small dots that are these noble metal particles that are the active sites. So this is how the overall catalytic process could look like. And now I'm zooming in a bit more into this area because this is where everything kind of happens in regard to reactions. So what a typical, let's say, process is, you have the reactants coming in by diffusion or transport, then they adsorb on the surface, on the active sites, they undergo a reaction, and the products are desorbed and, let's say, travel back. So that is a bit more zoom on the catalyst surface that either can be active as a whole surface or, as in the previous pictures, just single particles that are active. Now I would like to give you a few examples of this interaction, and that is actually this step here from a reactant coming in, interacting, and then leaving again. These are interactions between a molecule or a compound and a surface, and the nature of these can be categorized in being either physisorption or chemisorption. So these are two categories of interaction between gas phase and the surface. And if we start with the physisorption, that is more a weaker interaction between the two species, often determined by so-called non-specific van der Waals forces. It is often very fast process with a very low activation energy, so it is very easy for a molecule to approach and then have this very weak interaction. And you can also build up multiple layers, so you can have one molecule coming, covering the surface, and then the next layer and so forth. When we go over to chemisorption, this is a much stronger interaction, often connected with cleavage of a bond or a covalent bonding. It is also has a certain or a higher activation energy to happen as compared to physisorption. You can only have a monolayer because once you have really connected to the site, then the site is blocked and is not available for even more chemisorption species. So these are two main categories, and if we look a bit closer energy-wise, I have here an example from a very early book on catalysis. Here is the catalyst surface, and here we are going more and more out into the gas phase. So imagine a molecule is approaching the surface, then it starts feeling this van der Waals interactions. So it goes into a physisorption state, that could be here, where there's a minimum in energy. And then if it moves even closer, it has to overcome a certain activation barrier again, and then it falls into a chemisorption state, which is more stable, often connected with a cleavage of a bond, a dissociation, or making a covalent bonding. So this is kind of the two categories, physisorption and chemisorption. And the strength of interaction between molecule and surface is the key of the heterogeneous catalytic process. And I will dwell a bit more in the coming slides. Here it's a similar expression, energy here and a reaction coordinate. And first in the left case, we have two reactants. Often I give some examples, but it is also a generic illustration. So here it's carbon monoxide and oxygen are in the gas phase. If you want them to react to carbon dioxide, you have to overcome an activation energy if you don't have a catalyst. Then you could have one catalyst that interacts with between these two or with these two species, forming very stable adsorption of the two. Then you have to overcome quite a high barrier that they react with each other to the adsorbed CO2 that then desorbs to give you the product. This is of course not a very fortunate situation because this state is very stable. And that's why you would then rather try finding a different catalyst where the interaction is a lot weaker, like here in this case. So you have a weak adsorption, very easy reaction, and then a desorption. So this fine-tuning strength of interaction between this case and this case, this is the key to tailor and find the right catalyst. And there are a few models or concepts that are being used to judge and characterize this interaction strength. And one I'm showing here. This is a plot showing interaction of nitrogen with the surface and ammonia with the surface. And that is the illustration of ammonia synthesis or reaction of nitrogen to ammonia. Nitrogen, as you all know, is very stable. It's in the air, so it is not reacting very easily. So if you then introduce like these elements as an example, they have different interaction strengths with the nitrogen molecule. Like nickel has some interaction, is adsorbing nitrogen, stronger with cobalt, even stronger with iron, and if you go further, nitrogen is stronger and stronger adsorbed. Of course, as you saw before, it has to be a balance. I don't want to have nitrogen being very strongly adsorbed because then I cannot react further and desorb it. So anyway, so this is the first leg of the adsorption strength of the reactant. Then imagine you have made ammonia and you need to desorb it. So also the interaction between the surface and the product is quite important. And here it's kind of the opposite way for these specific elements. So iron keeps ammonia with a certain strength, and then this is weakened when you go further towards the other elements. And as you see here, there is a kind of sweet spot where it seems that nitrogen is adsorbed with a certain strength, then you form ammonia, and ammonia can also be released again. And this is a kind of typical illustration of how this balance has to be achieved between adsorption, activation of the reactant, and then release of the product. And these often form this type of curve, which is then called volcano curve, as it looks like a volcano. And the elements on top of this would be the best elements for the specific reaction. And now I'm showing also here. So here on this side, we have not really the right adsorption strength with the reactant, while here we also need to release the product. So this is a concept, the volcano curves, that characterize, if you plot it versus different parameters, could be adsorption enthalpy or other ones, electronegativity and so forth, then you can find the right best suitable catalyst for that specific reaction. So interactions are quite important, and that brings me to the final part of this introduction, the kinetics. So how fast is then actually the reaction going on? This reaction rate you have seen before is typically expressed by R, reaction rate. And normally you say it's the change of a concentration or a mole related to the time. So this is like the very generic definition of a rate. If we have a homogeneously catalyzed reaction, this value is often related to the volume of the reactor, to make it more specific. And if you go to heterogeneous catalysis, this reaction rate can be related to many different parameters. Could be catalyst surface area, S, catalyst mass, M, or even the number of active sites. And then it gets a specific name. You often call it turnover frequency. And that is also kind of expression of a reaction rate, now related to the really number of active sites. So it's a very specific number. Remembering that this catalytic reaction process or catalytic process is composed of many single steps that all can determine the overall reaction rate. For now, I would like to focus on this part, which is often the most decisive part, and this is what I can also change by selection of catalysts. The other diffusion are often related to pore size, channel sizes, and so on. So it's more structural rather than a chemical or physical phenomenon. From the many steps I mentioned, that the slowest in all these steps will determine the overall reaction rate, and that will also be the step that you can influence or that you would use for tailoring the right selection of reactor and of operating conditions. Going a bit more into detail now. We have involved adsorption, desorption, reaction processes. How do we quantify them? Typically, adsorption, desorption are expressed by a constant, the adsorption or desorption constant K, that expresses the equilibrium between a species in the gas phase. The star is typically used for an active site that is empty or free, and then the adsorbed species I. So here the equilibrium is expressed by the constant. Another parameter that is important is the surface coverage, tau. That means how much of the species I is attached to the surface. If you talk about gas phase concentrations of reactants, you are using concentrations or partial pressures better. And then deformation of the product is kind of related to a reaction rate constant K. So these are the quantitative parameters that are describing your reaction kinetics, typically involving different types of elementary steps, adsorption, desorption, surface reaction. To make it a bit more complex, there are different ways how a reactant can interact with the surface. We saw before it's physisorption, could be chemisorption, different strength. There are also different natures. Like if you have more than one reactant, we have two basic mechanisms called after people, Langmuir and Hinchelwood, or Ely-Riedel mechanism. The first one we have two compounds, molecules that react to AB. You can have both of them adsorbed at the surface, then they react with each other and the product is desorbed. So this is the first mechanism. The second is that you only have adsorbed one species. The other comes from the gas phase and reacts from the gas phase with this adsorbed species. Product is again desorbed. Why is that important to know? Because that actually changes the rate equation or reaction rate equation as shown here. If this is the mechanism you have at hand, then the reaction rate is proportional to the rate constant and the coverage with species A and B. So the concentration of the adsorbed species are determining the reaction rate. However, if one is adsorbed and the other from the gas phase, then it's no longer the adsorbed species B, but the species B in the gas phase that you express as a partial pressure. So it has quite a big impact on how the equation looks like and also what are your parameters that you can change to increase the reaction rate. Like here, I don't see in this equation the concentration of adsorbed species B, so they don't play a role for this reaction. However, the concentration in the gas phase, they play a role for reaction rate. While here, the gas phase B or A species don't play a role for the reaction rate, only the adsorbed species. So that is actually then also quite important to know in order to know which parameters I change in the reactor to achieve the highest conversion, the fastest reaction. And then to give you a few of the examples of these different interactions or mechanisms, there is a table here where you have different elementary steps. You already know adsorption, desorption, reaction. Then there are some examples for compounds where this is actually utilized in real life. And then a bit more generic, like with AB, maybe sometimes easier to understand. For example, the first one, you only have an adsorption site, a star reacting with ammonia from the gas phase, forming an adsorbed ammonia. So this is just an adsorption. There is no bond formation or bond cleavage or dissociation involved. While here you adsorb hydrogen molecule on two surface sites, and together with the adsorption, also the molecule is split into atoms. So here you have actually two processes, a dissociative adsorption. And the reverse, you could also have, like here, case adsorbed oxygen atoms on the star, and you are forming oxygen molecule, and you leave two free empty surface sites. So these are also a few more of the examples of adsorbed species that react with either from the gas phase or with another adsorbed species. So important to know what is happening on this detail level to be able to understand and to tailor the reaction. And you can determine these things experimentally, and I will come back to that in a minute. So coming back to adsorption, desorption, reaction, different mechanism, it is important to know what is happening to establish the right reaction rate equation and to be able to determine how do I actually design my system. And the final slides will be devoted to experimental investigation of this reaction kinetics. There are different opportunities, and I will start with a discontinuous one on the left-hand side. Two example reactors I can use are shown here, so-called batch reactors. There could be just a reactor where the catalyst is in this red layers, often stirred to have a good mixture of the gas phase. And here in this case, you have a recirculation of gases to have a good mixture between gases and the catalyst. And then with this setup, you can follow a mole concentration over time. And if you are watching a reactant, you will see that over time the reactant concentration is decreasing. So this is one opportunity, and from there you can derive the reaction rate equation as we have seen before. Another opportunity are continuous reactors, and I've also shown two examples here. This one is a recirculation reactor. Again, it's very much look alike this one. However, here, please observe you have an in and an outflow. So you have actually a continuous addition and removal of gases, so a flow through actually. The same happens here in a plug flow reactor where you are flowing your gases over the catalyst bed. And here in these cases, when you then plot, then actually you don't see a change of the reaction concentrations or reactant concentrations. As soon as you are putting a certain number of moles per hour or second over the bed, there will be a steady state, and corresponding to this flow, a certain concentration will establish here, which remains constant as long as the flow is constant. So in a way, you will have just one point in the reaction rate equation. Only if you then change the flow rate, that means you are changing also the time the molecules have to reside at the catalyst, you actually change concentrations. And in that way, you can obtain a similar correlation here that you just have in one experiment by following time. Here you need for each point to adjust the flow rates. And then this is now plotted for the formation of the product. And then you also can establish the well-known reaction rate equation. And depending on the like how fast the reaction is or the nature, you can choose one or the other reactor concept. In order to get smarter, you can vary all the conditions, concentrations, flow rates, temperatures, and determine kinetics, activation energies. And in that way, you also will see which is the determining step that determines the overall reaction, and then, as a consequence, design your system. To summarize catalysis, catalysts decrease activation energies and are not consumed in the course of the reaction. Catalysis is involved in between 80–90% of all industrial processes and products that we are having around us. Most of them are made via heterogeneous catalysis. The process of catalysis is very complex, consisting of many individual steps that involve transport, adsorption, desorption, reaction, interactions, and so on. And determining the kinetics and what is the slowest step in all this very complex network is important to be able to design your system in the right way to obtain the highest yield and selectivity of your desired product. With that, I'm finishing my short introduction. Thank you for your attention.